Well, thank you for watching this live session. I appreciate you all turning into view. Uh, I apologize for being a few minutes late, but as with life, sometimes unexpected things happen. So, let's get right to the review. I know that your time is valuable and you probably want to go do fun things this weekend. So, and let me bring up what you will need to know for the final. Alright. So, first of all, we are going to talk about uh, motion diagrams. Okay, so let me take a look. What do we need to know? First of all, let me say that I've really enjoyed this semester. It's been a really great semester. I've enjoyed interacting with all of you, even though it was on Zoom. I hope that when we're back in SLU, you will come by my lab and say hello. That would be really great. But the test is going to be through on chapters 1 through 5. And then we skipped up ahead to chapter 9. So then it'll be 1 through 5 and 9 through 13. Those are the chapters that we covered. Okay. So let's start in the beginning. What better place to start? We're going to start at chapter 1. And we need to know what a motion diagram looks like. Okay, so first thing you'll need to know are motion diagrams. So what if something is accelerating or traveling at a constant velocity? What would the motion diagram look like for that? So for acceleration and constant velocity. So if I asked you to draw the velocity of a particle while it was accelerating, what would it look like? Or if the particle was traveling at a constant velocity, what would that motion diagram look like? All right, so let's draw a couple pictures here. Let's say a particle is traveling at a constant velocity. If we were to draw in time, then the particle would travel a certain distance every, say, second, and that wouldn't change. So if we were taking pictures, then the spaces, the time between each of those positions wouldn't change, and it would be evenly spaced in time. It would move the same distance per second for the amount of time. So this is at a constant velocity. If the particle was accelerating, it would look something like this. Every time we took a picture, the particle would be moving farther apart. Okay, so this is what it would look like if it was accelerating. So here, we'd start off, and we'd only be covering a certain distance, and as we accelerated, the distance between the pictures would be increasing. So understand what motion diagrams are like. Then we need to think about for a projectile. Okay. As we throw a rock up in the air, how does its position vector change, and also its velocity vector? How are those changing in time? Okay, so you should understand which direction the velocity is moving, or what does the velocity vector look like? What does the acceleration vector look like? How do they change with time? Oh, there we go. And look at my drink. Oh, it's invisible. It's actually green. It changes colors. So if I put my finger there and I warm up that position, maybe here. See, if I put my finger there, it doesn't work. Okay, well, it turns green when it gets cold. Okay. All right. So let's see here. All right, moving on. Sorry about that. Express. Oh, okay. Yes, know how to calculate velocity. This is probably more important than the motion diagram. So if you know the original position, if you know a position at some time, you should be able to find its velocity. So if I tell you that it had a position at a specific time, and it moves to another time, and it moves to another position in a certain amount of time, you should be able to find the velocity. Okay. Then you should know what acceleration is. How can we find the acceleration? So if the velocity changes, how would I get my acceleration? So velocity, acceleration, very important. Let's write those down. So velocity, acceleration, and position vectors. Hopefully you all remember what a vector is, and you should be able to find its magnitude. So find the magnitude of a vector, the angle of a vector, and say the different components. So x and y components of a vector. And you should be able to do this for velocity and acceleration and position. All right, position. Okay, so you should be able to, in Cartesian coordinates, completely dissect a vector, find its magnitude, its velocity, and its x and y components. Okay, so what else do we need? Yes. Who is watching on YouTube? Maybe no one. That's okay. Maybe you'll watch it later. Okay, so let's see. Let's test out the chat. If you have questions, you can ask a question. Ask questions here. I can respond to your questions. Does it show up? Yes! You can ask a question. You'll get that later. Okay, well, let's go back to the live chat. Alright, what else do we need for the final? Alright, so we got a lot of acceleration. If you know a position versus time graph, or a velocity versus time graph, be able to find its velocity or acceleration. So for example, let's say, let's take a look here. And I'm gonna, hopefully this is not recording. Change in volume, there we go. Okay. So let's say we have a plot here, and this is velocity versus time. We'll put on units here. 1, 2, 3, 4, 5. This is in meters per second. And then here's our time. 1, 2, 3, 4, 5, 6, and so on. Okay, so there's my this is my plot here. How could this is velocity. So our velocity plot, meters per second. Okay, so based off of what I've drawn here, how could we find the acceleration of this plot? All right, so we know we need to find the slope because we know that acceleration is delta V over delta T. So that means if we find its position for 2 points, we're going to find rise over run. This will tell us what the acceleration is here. So let's just look at our numbers here. All right, so it looks like here, okay, and I completely made up these numbers, our rise over our run. So this is our first point here. We'll put it right there. Then our second point will go out here, okay, and we'll say that that is 5 and 4. Okay, so we'll have 4 meters per second minus 1.5 meters per second. Okay, and then we'll subtract our time. So this was 5 right there. Okay, so there's our time. So we'll have 5 minus 2. That's in seconds. Okay, so the difference here, we made it up to 4 meters per second. So it's going to be 2.5 divided by 2.5 meters per second divided by 3 seconds. Okay, so then we'll say 2.5 divided by 3. So 2.5 divided by 3. Just using my handy dandy iPhone calculator. 8.833. There it is. 0.833 meters per second squared. Alright, so we used our plot here, and we found our acceleration based off of what we saw on the plot here. Alright, and I'm going to move my head because my face is not important. What is important is that you see what's going on here, not my ugly snout. Okay. Moving on. There we go. Let me close that. Okay. Oh, we've got a viewer. Welcome, viewer. Oh, thanks for watching. All right, moving on. So we are moving into chapter 2. All right. So, chapter 2 is more acceleration. So, if you say, let's see. If you say, all right, your velocity is changing by this much in a certain amount of time, what we did here, then you are going to need to be able to do this to find its acceleration. So we pretty much did this. This is a good problem. You should be able to do this for velocity too. So if I gave you position as a function of time, find the velocity. Very similar. All right, let's talk about projectile motion. Okay, so all right. So let's say we have a projectile and it looks something like this. Okay. We'll draw it at a height like this. Okay, so here's our projectile. Okay, and what do we have? Okay, so here is X and here is Y. And let's talk about velocity and acceleration vectors. Okay, so the key to remember is that there's a couple things that are constant, and there's some things that change. The thing that is always constant is the acceleration due to gravity. Okay, so at any place, we could draw the acceleration due to gravity at any time here. Okay, acceleration due to gravity is always pointing down. Okay, it always points down. Okay, it doesn't change. The gravitational constant is it's always, that's why we call it a constant, because on the surface of the Earth it doesn't change. Another thing that's constant is for a projectile the x velocity. Okay, so once our projectile starts off with some x velocity, that doesn't change. Okay, so our x velocity doesn't change. This is like if you fired a bullet from a gun, or a Nerf gun would be better. No, not a Nerf gun. A pellet, something without wind resistance. So a BB, non-lethal. Let's talk about a BB. The BB gets fired. Its x velocity doesn't change. It always stays constant. So my x velocity is going to be the same over here as it is over here. Same here. Right? Vx is always the same. That doesn't change. Acceleration is also constant. Always 9.8 meters per second squared, pointing down. What does change is my y velocity. Okay? If I drew my velocity vector here, my velocity vector would look something like this. Okay? So here's my vy velocity. As this thing gets higher, okay, my velocity vector looks like this. Vy is getting smaller. Okay? So see right here, vy is much smaller here, and up here at the very top, Vy equals 0. Okay, all of its velocity, it only has x velocity up at the top. When we get down here, now my the direction of my velocity has changed, and the magnitude is also changing. Okay, so vx or vy right there. Okay, so as you go up, vy is positive. When we get to the top, there's no more y velocity. It's still traveling forward, so there is an x velocity. X velocity is constant. Acceleration due to gravity, also constant. Alright, so there we have our projectiles. So, for a problem like this, if you want to find the time it takes for the particle to travel from here over to here, you would need to find the time that the particle is in the air. Okay? You do that with your y equations first. Okay? There's several different ways that you can do it. Okay? My go-to equation is y equals y0 plus v0t plus 1/2 at squared. Okay? This equation is good for projectiles. If you start at a different height here and you come back down, this will tell you the time. Okay? Now, on a problem like this, there are two instances where you'll be at the same height. Okay? Over here and over here. Remember the local trout problem. The fish jumps up and it comes down, so there's two positions here. So you get two times that would be at the same height. To get over here, that would be the later time. So once we know how long the projectile is in the air, then we could solve for how far it travels. Okay, so find the time with the y equation. Oh, there's my go-to equation. Okay, once you've found the time with this equation, now you can say, what's my x distance? This is x equals vt. And this is some really important physics here because there's no acceleration in the x direction. Acceleration only happens in y. We're going to ignore drag. We're not going to worry about wind resistance here. Okay, so we're going to get rid of that. All right, so yes. So this is a very, very important concept. So solve for time, then we can find our x distance. Okay. Moving on. What else do we have? What else will you need to know for the exam? Vectors. Let's talk about vectors. Okay? So let's draw some vectors here. Okay? We can do math with vectors. What could be better on a Friday night than vector math? Oh, I love it. I have a vector A and a vector B. Let's say A looks maybe like that. There's vector A. I don't know, I'm just drawing random vectors. This is the weekend. You can draw whatever vector you want. Okay, let's say B. What does B look like? B looks like this. There's my B. So, if I said A plus B, what would that look like? What do you think? All right, A plus B. All right, so my vectors are right here. I'm going to draw it up here. Okay, there's my first vector. B is going to look something like this. Yes, A plus B, and then it's going to give me a new vector right here. Okay, there we go. That's my new vector, C. So I could say A plus B equals my new vector, C. Alrighty. What if I said A minus B? What about no, let's say B minus A. Oh. Now this is getting even more awesomer. I don't think awesomer is okay, we've got B here. Let's draw B. There it is. B. There's B. Let's say minus A. It's going to reverse the direction. It's going to go the other way now. We can move it over here. We can move it. Let's put it A. B minus A. There it is. We've reversed the direction. Now we're going to have a new vector here. D. Yes. This will equal my new vector. D. Okay. Review vectors. How do you find the magnitude of a vector? How do you find the angle of a vector? How do you find its components? Alright, so let's say, yes, review your vectors. How do we do vector addition? What if we had 3 vectors and we add them all together? How would we do that? Alright, moving on. Alright, so what if, yeah, we need to know velocity vectors going at different angles. Okay. Alright, what do we need to know? Oh yes, what if we have a case where someone or something is rolling down a hill? Let's say, here's a Pinewood Derby car. Okay, it's going down the hill. Okay, let's say I know its horizontal velocity here, Vx. I know what it is. Okay, and I know the angle here. Okay, how would I find V? What's the magnitude of V going to be right there? Okay, so I don't want to give everything away. That would just be no fun. Okay, we talked about projectiles, how far they travel. Alright. Let's talk about drag with a projectile. Okay, so let's say we launch our projectile now. Okay, so our projectile gets fired up in the air like this. So now if we have drag, we're going to have our acceleration is going to go down this way, and our velocity now is going to be changing, and the force of drag, which way is it going to be? Is the force of drag going to be in the direction of its motion, or would it be opposed to it? So figure out which way the force of drag is going to be go, and what formula do we use for the force of drag? Write that down on your equation. Okay. What if we have a changing force? That was a problem that we did with the Lamborghini. Take a look at that problem. So the Lamborghini starts off. Hey, here's my Lamborghini. I'm gonna draw an awesome Lamborghini. Oh, there's my Lamborghini. Oh, yeah. Oh, yep. There we go. Whoa, let's draw a spoiler. Whoa, there it is. There's my wheels. There's my front wheel. I think the back wheel's bigger. All right, there's a thingy on the side. Intake valve. Lamborghini. Boom. Okay, there's my Lamborghini. There's the wheel. All right, so let's say that our Lamborghini can generate some kind of force. All right, we know what... if the motor can produce a certain amount of force, okay, that force is constant. Let's say we know the mass of the Lamborghini without the driver. So let's say it is 1,200 horsepower, okay, and we know. Let's say we know the force. We'll put it in newtons, okay. I don't remember what the numbers are, but you should definitely review this problem. So the Lamborghini driver gets in. He accelerates at a certain rate. Then he picks up a passenger. What is the new acceleration of the Lamborghini once the mass has changed? Okay, so what is A if M changes? Okay, because once we add some mass in there, okay, the acceleration is going to be different. Now we have more mass. So maybe you felt this. I never had the experience in a Lamborghini. Although I did have a Nissan Sentra, and it was I was a little sporty, okay? But now I think this is probably a lot more pronounced, but when 4 people sat in my Nissan Sentra, I can tell you that it didn't quite have that kick that it did when it was empty. There's a lot more mass. Right? I'm sure my Nissan Sentra was just like the Lamborghini. Very similar handling and driving experiences. What is the acceleration if we change the force? Know that. Oh, no. Oh, sorry. Slight technical issues. Nothing to worry about. Alright. What else do we need to know? Oh! Free body diagrams. What are they? What do we use them for? Alright. So, imagine... What should we say? Yes, let's do it. Let's talk about the blue whale. Now, I'm not saying that blue whales will or will not be on the exam, nor am I saying that zombies on treadmills will be on the exam. Probably not zombies. There were no zombie questions in the test bank, but let's talk about blue whales. All right, let's draw our force diagram for our blue whale. All right, we did this problem in class. It was a good one. And I like drawing blue whales, so we're gonna do it. Yes, there's my fluke. Here's my fin with the tubercles. There, those are the bumps on the whale. And there he is. He's a happy whale. He looks happy. He's like, I'm eating lots of krill. Let's draw the force. He's got some thrust. The thrust is going this way. Okay, there's also some drag. Okay. He's got the force of drag there. His thrust is pushing him onwards. And he has some weight. Blue whales, they're kind of heavy. Okay. And he's also got the buoyant force. Yes. We've done it. We've drawn our free body diagram. Think about free body diagrams. What other kinds of free body diagrams could we draw? Maybe a car accelerating, an airplane taking off, what else? What other ones? Maybe a sloth sliding down an inclined plane. Why a sloth? Why not a box? Why not a sloth? I don't know. Think about the different problems that we did, but be able to draw the free body diagram. Don't forget about friction. Don't forget about drag. Don't forget about the normal force, the thrust, if there is any. I don't think we did a problem with sloth, but you get my point. All right. Free body diagrams. Tension. What is it? How do we find it? We had a problem. We had several problems with tension. I think there was one where... Yes, it was a violin. The violin problem. We review the violin problem. Yes. We had a violin. We pulled the string back with the bow. What was the tension in the strings? That would be a good problem to know. Why am I telling you this on the review? Maybe it's important. Review the violin problem. Yes, tension on a string. Okay, what else do we have? Yes, tension. Yes, tension is also good for objects hanging from ropes. You should know what the tension is for a mass. Maybe one floating in water. What's the tension of a mass floating in water? We also did, I think, a considerable amount of friction. Okay, so what if something is sliding on the floor with friction, or it's not sliding and there's static friction? Be able to calculate what the forces are on that object. So if I push on an object, how much force does the object push back on me? What if the object is accelerating? Is the force that it pushes back on me different than if it's still? Okay, so definitely know frictional forces. Yes. All right. What else? We talked about work. How do we find work? Okay, so we said that uh, let's say we apply a force to an object over a certain distance. Okay, so maybe a oh, I was almost gonna do a crate on a block, but then I thought about what else could we use? Let's just do it with the crate. All right. So here is my crate, and if I push my crate with some force here, okay, and there's some force of friction pushing back on me, and I know the distance here, okay, here's X, how do I find the work? How much work did I do? Okay, so if I push on it, then how do I find my work? What's the formula for work as a function of distance? Okay, so we'll have work is equal to force times distance. Okay, what else? What else do we need to know? All right. Let's see. We talked about. I think we did things in the homework with springs. So, how do we find the energy stored in a spring? So, energy stored in a spring. Okay. And in general, potential energy. Potential energy. So, potential energy and also kinetic energy. Okay, so let's say a skateboarder starts up here at some height. Okay, so here's my skateboarder. Okay, and he's got some potential energy at the top here. Okay, if we know what the height is and we know what his mass is, then we should be able to calculate our velocity down here at the bottom. Alright, oh, and you can't even see it. Ah, all right, there's my skateboarder. Let's say my skateboarder starts up here. Okay, so here's my skateboarder. Okay, so there's my skateboarder, and he's got some potential energy up here at the top. Okay, MGH. Okay, I think we had a problem where we calculated if the center of mass, if we know the distance here, okay, then we should be able to find the skateboarder's kinetic energy at the bottom. More specifically, what is his velocity down here? Okay, so we know our potential, then we should be able to find the velocity down here. Okay, so what else do we have? Then we talked about using energy. So if you know that so if you have a certain amount of energy, some power source, maybe it's food or a battery, then if what is the efficiency? So efficiency is so how much of that power can you actually use for something useful as opposed to how much is being supplied. So you should know about efficiency. Okay, then you should know about metabolic power and what happens when things, so metabolic power. Okay, all right, so if I was, say, bicycling at a certain speed, and that would mean for the whole process, I would need to supply a certain amount of power. Some of that power I could use for useful work, but most of it would be lost in thermal energy. And then we would say, well, how efficient is that process? Well, it would be the amount of energy I used to do the work as opposed to how much I actually had to supply. So how much power went to actually doing the work versus how much power, metabolic power, I had to use to actually do that. So humans are about 25%. So if I need to supply, say, 80 watts of power, then I would have to have more than that. Okay, so let's say, so if I need 80 watts of power and I am 25% efficient, okay, so then I would say, okay, my power to pedal the bike, I need 80 watts. So I divide that by 0.25, that's 25%. So then it would take me 320 watts. And that's, I think for a bicycle, it's actually 370 watts, but that's close enough. All right. So then we also talked about ideal gases. So if I have an ideal gas in a container and I supply some thermal energy, how much does the temperature change? How much does my pressure change? Okay, so we have PV equals nRT. We also want to know about the kinetic energy of the gas. Okay, so if say I tell you this amount of gas has a certain kinetic, a certain temperature, what is the corresponding kinetic energy? So, or if I said, all right, I supplied this much thermal energy to the gas, it's at this temperature, how much kinetic energy does it have? All right, then you should know about length, contraction, and expansion. Okay, so if something has a certain length and it changes temperature, depending on the amount of temperature change there is, the length will change. So we want to know, okay, about length, contraction with temperature. How does the size of a material change with temperature? Then you should also know about the buoyant force. Okay, so why do things float? Let's see, what else do we need? Okay, then we also talked about fluids. Okay, so we did a couple problems where we dealt with fluid flow. Okay, so if I have, say, a pipe here, okay, and my liquid has a flow rate over here, okay, and I know what the velocity is over here. So if I know what my V1 is, how do I find V2 if I know my area here? Okay, so if I know my surface areas, okay, how can I find the velocity of my fluid as the size of my pipe changes? So as I go from a bigger area of tube to a smaller one, what happens to the velocity? How could you calculate what that is going to be? All right, so we also want to talk about buoyant force. Let's see. And this brings us finally to the end, which we talked about momentum and impulse. How do I find momentum? So let's say two objects collide. That was the problem of the mosquito. So a raindrop hit our mosquito. Then we want to be able to find what was the impulse during that event. If two objects collide, so say they stick together, what is the new velocity of our particle? So if, say, one object is stationary and it has some mass, and another object hits it, what is the new velocity of that system? So we want to be able to find our momentum before the collision and then after the collision. So we want to get our change in momentum. So you should know about momentum, impulse, and then what's the force. So if we have a certain impulse, okay, how do we find the force from that event? So if I say had two objects where one was hard and one was soft, So like that, there was that example in your car, okay? So let's say I wanted to calculate the different forces for a squishy material and a hard material, okay? How would I find the maximum force based off of my impulse? So if I know the time of collision and I know the change in velocity, then how would I find the force for that event? Okay, so that's about pretty much it. I think that's all of what we could cover this semester, and I apologize for having this take so long. But so if you watch this, then you'll know the things that are important for the exam. So thank you for watching this live stream. This might be my last transmission. So have a great weekend, and I hope that you will all come by when the lab opens up again. And thanks for watching. So if you have any questions, please send me an email. Thanks. Bye.